Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 80. Now, in the previous class, I had introduced you to the concept of planetary chemistry, and we were discussing about the rocky planets and the gassy planets. So the rocky planets are, Mercury, Venus, Earth, and Mars. And the gassy planet, or gassy perhaps, are Jupiter, Saturn, Uranus, Neptune, and Pluto with a star, because Pluto is it's a dwarf planet. All right, and we saw why the gassy planets stay away from the sun. It basically has to do with the temperature. See, the gas molecules can just run away is a colloquial phrase. They can fly away quickly, and a lot of them accrue together. Condensation temperature is not high enough. They all, when the mass builds up, they stay far away from the sun as the temperature is lower. But for the solid particles, for the species which are condensed, they are close enough to the sun. Now, that these are rocky and that these are gassy is also evident by calculating the density of these planets. So the densities are the density of a planet can be defined in a rough way as the mass of a planet divided by, just assuming it is a sphere, basically that is density, mass by volume, assuming it's a sphere. Okay, so this is how you define the density of a planet, and it is expressed usually as grams per centimeter cube. Now for Mercury, Venus, and Earth, okay, the density is roughly between 5.3 and 5.5 gram per centimeter cube. I can give it to you as a homework to find the exact values. But so these are dense, and this indicates that these are indeed made of rocky materials predominantly. That of Mars is slightly lower. It is approximately 4 grams per centimeter cube. All right. So these are the densities for the rocky planets. But for the gassy planets, especially for Jupiter and Saturn, I think it's 1.2 and 0.9. I'll confirm. 1.4 for Jupiter and close to 0.7 for Saturn. And interestingly, Uranus and Neptune are slightly denser. They're, I think, of the order of 1.3 and 1.6. 1.3, 1.6, and Pluto, despite being small. Okay, so clearly, we have a beautiful demarcation. The density values are larger here, and they are much smaller, indicating that the material is much more tightly packed in the rocky planets than the gassy planets. Now, this has implications. What are the implications? The implication is that the most significant implication is that your until Mars, okay. I mean, until Mars, when I say starting from Mercury, the role of the atmosphere, well, What do I mean by atmosphere? Atmosphere is the envelope of gas surrounding a planet, let's say. Now, this could be thick or thin. So, until Mars, the role of an atmosphere is to, let's say, in some ways, protect the solid structure from the rays of the sun. All right, please note this point. So what is an atmosphere? I'm using the phrase atmosphere to refer to the gaseous envelope that surrounds the solid core of these predominantly rocky materials. Okay. However, notice the point that the atmosphere on Mercury is very thin. Okay, in comparison with Earth, there is not much of a gas cover for Mercury. Please note this point. But whatever it is, the rocky structure is in some ways saved from harmful radiations emanating from the sun by this atmosphere, however thin it is. All right. It is most predominantly noticed in the case of Earth. As we know, right? There are a lot of harmful radiations which are absorbed by ozone and other molecules in the atmosphere which don't let them enter the Earth. Okay. So as a result, the solid structure remains mostly intact. However, with the gassy planet, now the solid core is very, can be ignored. Okay, the solid core is very thin, can be ignored. That's why it's predominantly gassy, of course. But that is not to say that there is no solid in planets such as Jupiter and Saturn. Just that the solid part is very thin. And the so-called atmosphere makes up the entire planet itself. Okay. So this is a major implication. This is a major implication of the densities. Okay, the densities and the idea that your atmosphere can, in some case, protect the rocky layers, but in the other case, the atmosphere is the major component itself. Okay, so please note this distinction, and that is why whenever any space agency, be it NASA, ISRO, or the European Space Agency, JAXA, or any agency, right? Whenever they look for life, they don't look for life in, say, for example, Jupiter or Saturn, because it's completely full of gases, right? You need some solid structure. The way life is evolved on Earth, right? The way we understand life, we need some solid foundation along with liquids also. But in a belt of, in a region which is completely full of gases, life is impossible. Okay, so this also implies that your Jupiter, the gassy planets in general, are absolutely uninhabitable. In other words, it's not meaningful to look for life, in these gassy planets. Now, having said this, though, there is one very interesting aspect. Okay, now while these planets themselves are completely uninhabitable because they're full of gases, right? There is this specific satellite of Saturn. Okay, yet there is this satellite. Well, when I say satellite, I'm talking about some celestial body which orbits around a planet. Okay, right? More colloquially, you can call it a moon of Saturn, called Titan. Okay, right? Now this Titan is a very interesting planet. It's a very interesting entity. Okay, I'll tell you why. It is not a planet, it's a moon of Saturn. Okay, I'll tell you why it is interesting. Now Titan is interesting because, see, it is roughly half the size of Earth. Okay, roughly half the size of Earth. The temperature in Titan ranges from roughly, say around 70 Kelvin to 190 Kelvin. Now this range is important. The gassy planets are very cold, okay? But in Titan, the temperature range is approximately 120 Kelvin, which gives rise to a variety of chemistry, okay? Implies variety in the chemistry. And in particular, it has a prominent atmosphere, okay? So Titan has predominantly comprising of 90% nitrogen. Hey, nitrogen is also commonly found on Earth, right? And not just that, it also has a significant amount of methane. Okay, so methane, actually presents some very interesting atmospheric chemistry in Titan. What methane does is, like we discussed in the case of comets, there is interesting photochemistry possible in this region. Methane in Titan surface, we're talking about gas phase, can undergo homolytic cleavage to form methyl radical and hydrogen atom. And interestingly, this methyl radical can further give rise to your two types of this is called as methylene. Okay, you can get what are called as carbenes from this. So you get two different types of carbenes, and they can further undergo dissociation to give CH radical. And do you recall CH radical? That was in fact the first one of the first molecules to be detected in space, in the ISM in fact. Okay, remember in the 1930s we were talking about McCarroll's work and all that, right? Okay, so it gives rise to very interesting atmospheric chemistry, right, which is somewhat similar to Earth. So this similarity to Earth, right? When I say Earth, right, I'm talking about Earth's atmosphere, not on Earth itself, okay? So this facet has had astronomers and astrophysicists be actually fascinated by the Saturn's moon Titan. That, oh wow, there are quite a few similarities between Earth and Titan. It doesn't stop here. So beyond that, in fact, the most unexpected and a very exciting discovery in Titan was that Titan is the only, right? I mean, see, whenever you use the phrase only, you have to be very careful, right? So, I mean, as of today, we're talking about even until 2024, Titan is the only place in the solar system to have a substantial area covered by liquids besides Earth. So this is a major point. It's a very, very important point. In fact, if you notice, all along in this course, I have always been only talking to you about solid phase or gas phase, right? Liquids were never given that prominence because, as we saw perhaps in the first 7 or 8 lectures itself, the phase diagram dictates the existence of the phase of a substance, right? And under interstellar conditions, well, liquid phases typically do not exist. And even in the study of meteorites, the solids mattered. And in the study of comets, the volatile gases mattered. It was never the liquids. But despite all of these aspects, in Titan, a significant chunk of liquids have been found. These were detected by prominently, 2 spacecrafts. One was NASA's Voyager. I mean, this was way earlier to our generation. We're talking about late 1970s, perhaps. And more recently, Cassini, which was perhaps sent around 2004 or 5. This is from NASA and this is from European Space Agency. So they found that it has a lot of liquid. But hey, I was very careful in stating that Titan contains liquids, not water. Okay. In fact, you would be surprised to know what these liquids are made of. Can you even guess? Well, these liquids are made of predominantly lakes of liquid ethylene. Sorry, this is called as ethane, not ethylene, sorry, ethane. This is predominantly liquid ethane. Can you imagine that, right? Well, on Earth, what is this? Methane, ethane? It is actually a gas. Considering the Earth's conditions, by conditions I refer to pressure and temperature, it's a gas. But here it is going to be a liquid. So even though, it has a lot of promise in terms of containing substantive liquids, the liquid is not water. It is some hydrocarbon. And therefore, this tells you how different, the pressure, the pressure and temperature the pressure and temperature are in Titan with respect to Earth. Nonetheless, it is a very interesting discovery that liquids have existed. Liquids do exist in Titan alongside Earth, which is the only place to have liquids. All right. So that is the key observation about Titan. Now, the next topic we'll be discussing, as far as the planets are concerned, is it's more of a general knowledge type fact, but an important one. It is that, okay, recently, when I say recently, I'm talking about just a few years earlier. Okay, this is 2024. Pluto was declared to not be a planet. Okay. The question is why? Why is it that Pluto was not declared to be a planet? In fact, for generations, I think Pluto was perhaps discovered in between 1910 and 1930, somewhere around this time, and it was discovered. It was called a planet, rightly so, because it does orbit around the sun, and it had a sufficient mass, to have enough gravity. Okay, to have enough surface gravity. So both these criteria meant that Pluto was indeed a planet. But suddenly, I think the discussion started perhaps in the early 2000s or something. The International Astronomical Union, IAU, they decided that Pluto is not a planet. The reason is that in the vicinity of Pluto, well, when I say vicinity, I'm talking about ranging up to thousands of light years. Okay. Lies or lie the Kuiper and the Oort belt of comets and lots of other asteroids. Now, because of the proximity of all these asteroids and comets, etc., etc., Pluto has been suggested to be a dwarf planet. Due to the presence of these comets, I'm continuing from here. It is not easy to define a fixed mass for Pluto at any given point in time, because there is a constant bombardment of Pluto by the comets, etc., etc. So there is constant mass transfer happening in and out of the planet, much more than, say, like Earth or Mars. Okay, due to these, when I say these, I'm referring to the presence of a lot of asteroids and meteorites, a lot of constant mass transfer occurs. Okay, a lot of constant mass transfer occurs from in and out of Pluto. And as a result, due to this constant mass transfer from Pluto, it's not easy define the mass of Pluto. Like, say, you would do it for Earth, for example, like so it is not just the mass, it's also the morphology that changes, and consequently it's the ellipsoidal path around the sun, the ellipsoidal orbit, that also changes. So considering all these reasons, and especially noting that it's anyways a tinier planet vis-a-vis the tinier entity vis-a-vis the other 8 planets, it was decided that, okay, Pluto need not be called a planet. So this is a huge change, right? In fact, elementary school textbooks have to be rewritten on this basis. Okay, so this is one reason why Pluto is not considered a planet, because of constant bombardment with all these meteorites and asteroids, etc., etc. Okay, so this was the next physical aspect about planets. The last one, for today's lecture is going to be the surface temperatures of planets. So when we consider the planets, if we consider them to be black bodies, okay, assuming black body radiation and LTE, which is a drastic assumption actually. So I feel use the abbreviation BB because black body, we've always been using it in this course, and also LTE to refer to local thermal equilibrium, right? The amount of radiation received by any planet, okay, the amount of radiation received, I'm going to use the symbol F, to denote some sort of a flux, okay. Is given by sigma times 10 to the power 4. This is what is called as the famous Stefan's law. Where sigma is a constant, something like 5.67 into 10 to the power minus 8 watt per meter square times Kelvin to the power minus 4. So this is some kind of a flux because its unit are in watt per meter square. Okay, so assuming black body radiation, the Stefan's law holds good. Okay, now under this assumption, one can, using this, one can compute the surface temperature. One can compute the surface temperature of the various planets. Okay, I have not told you how. Note. I won't give you further details. It can easily be done. You just have to consider, a specific cross section of any planet receiving this, and you have to find the flux from that. That's all doable. But again, due to a paucity in time, I'll just tell you that from this you can calculate the surface temperature. Okay, and it turns out that the surface temperature for some key planets are given as follows. Let's just call it T sub S. Okay, the surface temperature. Let's say, the planet, and this is the surface temperature. We'll start with Earth. Okay, so for Earth, it is given to be roughly, can you guess? For Earth, it happens to be around 288 Kelvin. Okay, and in comparison, for Venus, it is 755 Kelvin. Expected, right? Venus is much more rocky. So what would you expect it for Jupiter, for example, then? It should be a number lower than this, but by how much? It turns out to be 165 Kelvin. Okay. The only other important data point here is for, say, something like Neptune. The moment you go to as far as Neptune, this temperature drops to around 72 Kelvin. Okay. Oh, Mars is also important. Mars, okay, where there's a lot of interest to explore because it's our neighboring planet, right? It is around 223 Kelvin. So it's around closest to Earth, which is why a lot of space missions are also exploring the possibility of life existing on Mars. Okay, so the surface temperature is an important characteristic because it tells you, along with the surface pressure, about which we shall look into the next lecture. Okay, so the surface pressure and surface temperature tells you about how whether life may have been possible in some planets and whether it is not possible in some other planets. For example, you can straight away rule out Venus, Jupiter also, and Neptune, of course, yes, and Mars. Perhaps Mars is somewhat closer. So if you could get to Mars, maybe there is a possibility of life. So with this, I end this lecture. And what did we look into in today's lecture? The summary is that I was talking to you about the various physical characteristics of the planets. Okay, we started off by discussing the rocky versus gassy planets and their densities, assuming everything is a sphere, every planet is a sphere. And after that, we were discussing about some interesting physical properties of Titan, which made it an object of astronomical and astrophysical, also astrobiological interest to check if life was possible there. Followed by that, I introduced the idea of surface temperature, and I told you that the temperature of Mars is close enough to that of Earth. And with that, I end this lecture, and we'll continue with the implications of the surface temperature of Earth being 288 Kelvin in the next lecture. Thanks a lot and have a good day.